Hello everybody, my name is Giuseppe Brandi and I am a PhD student in Applied Mathematics at the King's College London. Today I will speak about a paper I have with Tiziana and Matteo, which speaks about clustering multidimensional data. So we will go through a short introduction on the topic, then we will go through the higher order hierarchical spectral clustering algorithm, which we are proposing. And then we will go through an empirical application and the results. And then we will finally conclude. So we have a lot of multidimensional data in economics, in finance, in network analysis, and in other related fields. But what we usually do, we reshape those multidimensional data sets in matrices or vectors, and then we analyze them in this easier form. The main drawback of this kind of approach is the huge loss of information. In fact, what we will do in doing so is to eliminate all the interconnections that we have across the dimensions of the dataset. And the second drawback will be that reshaping those multidimensional datasets in vectors or matrices will need to have much heavier models to analyze them. So we will not have any parsimonious model able to analyze them. And the final thing we want to contribute to is to establish a stronger link between the multidimensional or tensor research community and economics and finance. So the motivation is that we know that it's already difficult to cluster multivariate data, and it's even more difficult when we want to cluster multidimensional datasets. And this is because they have stronger intra and interconnections across the dimensions. So the question is, are we able to produce a tool which is able to cluster the data in the case of the multidimensional case? And the contribution we are going to give here is the higher order hierarchical spectral clustering, which is a method or a tool which leverages over two different algorithms. One is the tensor decomposition of the multidimensional dataset, while the second one is a hierarchical clustering algorithm. Now, decomposing the tensors and from which finding the factor matrices is quite different from just reshaping the tensor in the matrix. This is because in the tensor decomposition, the specific factor matrix that you find is related to the specific dimension of your multidimensional dataset. So there is no loss of information in this case. So as I said, we have two ingredients to our algorithm. The first one is tensor decomposition. So what are tensors? Tensors are just the generalization of scalars, vectors, and matrices to the higher order. And they're also called multi-way data or multidimensional arrays. We have a lot of examples of tensors or multidimensional data sets in economics, like panel data, time series of networks, or portfolio multivariate moment with value with moments higher than the second, like the co-skewness or the co-kurtosis. Or even in other disciplines, we have a lot of tensors analysis, especially when we deal with video or images. The literature on tensors is flourishing, and in the last 2 decades, tensor methods got a lot of attention, especially from the machine learning community. However, we are going to use the most use tensor decomposition or tensor factorization, which is the Tucker decomposition, which was introduced by Tucker in 1964, and it is also called the higher order singular value decomposition. Here we have an example for the three-dimensional case in which a third order tensor is factorized in a small core tensor and 3 factor matrices. Now you can use this decomposition for 2 main reasons. The first one is for dimensionality reduction. So let's suppose that this X tensor is 10 by 10 by 10, so 1000 values. And now you impose a core tensor to be a 2 by 2 by 2. So each of those matrices will be a 10 by 2, which means that you can approximate this 1000 values tensor with just 68 values. Of course, this approximation will not be quite good, but this gives you the strength of the dimensional reduction that you can achieve with those methods. The second motivation why you would use the Tucker decomposition is to study those factor matrices, which are the matrices for each specific dimension of the original tensor, while the core tensor will just give you the interconnection of each factor matrix of one dimension with the other ones. The Tucker decomposition takes the form of the N-mode product. So we have that the core tensor will be multiplied over, let's say, the first dimension with the first matrix, over the second dimension with the second matrix, and so on. And this is an easy way to replace matrix times matrix multiplication. So factor models in economics or econometrics start from a function of the data set of this form here, where we are trying to synthesize the whole data set with few components. And now what we can do with this is to, again, we can have 2 different approaches, is to try to study this factor loading matrix, or just use this to make better predictions. However, what is important here is that this equation here can be easily written in the N-mode product form, where the factor loading matrix multiplies the factor times series. Now this can be easily extended to the multidimensional case by using the higher order Tucker representation, in which now the X and the core tensor F are time series themselves, and is what we are using in our approach. What is important for us here is to analyze those factor matrices here, which are the latent space spanned by the original dataset on a specific dimension. Now, as I was saying, we have 2 ingredients. And the second ingredient of the algorithm is the hierarchical clustering algorithm. And here we use the dark bubble hierarchical 3, which is a machine learning hierarchical clustering method, which is able to exploit the topological property of a planar maximally filtered graph of your data set. And it is able to capture the most number of informative nodes in the graph, and then is able to use its 3 clicks topological structure to distinguish between separating and non-separating tree cliques and identify the clusters. Now, to use this algorithm, we just need two different matrices. One is the similarity or a distance matrix, and one is a similarity matrix. In this case, we use the Euclidean distance for the distance matrix and the Gaussian kernel for the similarity matrix, where now we are using the Euclidean distance over each factor matrix. So I here stands for the ith factor matrix. Now we can just wrap up the whole algorithm as a three-steps approach. The first one will be devoted to the Tucker decomposition, from which we extract the factor matrices. In the second step, we will compute a distance matrix and a similarity matrix for each of those factor matrices, and then we will input those in the DBST algorithm, which will give us back the optimal clusterings. This is in the same spirit of spectral clustering because we don't use the hierarchical clustering directly on the dataset, but on their factors. So for the empirical application, we will work on a dynamic food network, and the literature on dynamic food network is flourishing, even if it's not really developed yet. And the analysis was especially on trade analysis, on the fragility of the network, to understand if when we have some shock on food, which can propagate across different countries, and then to try to correlate the economic development of a country with the food import-export. Recently, two papers also worked on clustering countries with respect to specific products. So they basically got the multidimensional dataset and worked using just one slice by slice. But this approach will not explore the multidimensionality of the dataset. I will not be able to produce a synthetic proxy of geopolitical and economic interconnectedness that you can find with the method that we are proposing. So in our analysis, we are using the FAO trade network, which is an economic network in which you have the nodes, which are the import and exporting countries. Then you have the layers, different layers which represent the products, and then we have an additional dimension, which is the time. So in our case, we have 33 years of data with 128 countries and 137 products, which give us a fourth order tensor. Let's go to the results. So for the Tucker decomposition, so the first step of the algorithm, we need to specify how big is this core tensor. So to do that, we fitted the Tucker decomposition going from a one factor model specification to a 50-50-50 specification. And then we search for an elbow in a discrete type of plot to check which is the optimal specification. And doing so, we saw that the best configuration is given by 28 factors in both the import and the exports dimensions and 17 for the product dimension. It's important to say that for the DBHT, we don't need to specify any parameter because it already finds the optimal clusters. Now, going through the results, we can see that we have the European cluster up here. So we have a macro cluster here, and then we have 4 smaller clusters which are more related to their geographical vicinity, proximity, or to their trade, how much they trade together. While we have another European cluster here, which is mostly devoted to ex-Soviet Union countries and East European countries, which have much tighter relationships, both from an import-export trade point of view, and also from a geopolitical point of view. And then we have up here quite big Asian cluster in pink. Now, if you go to the export cluster, we have similar performance. We can see that we have here, up here, we have the macro European cluster. Now we have here the French-speaking countries, while here we have, again, in the top part here, in pink, violet, and purple, we have the East European countries and the ex-Soviet Union countries, while here in blue we have more the countries which are more on the south. And while here, down here, we can see that we have the Asian countries. Now, going through the product clusters, we can easily see that we have the vegetables cluster up here. Then we can see we have 2 meat-related clusters. One of them is more related to pig meat, while the other one is more a mixed kind of meat-related cluster. Then we have here a beverages cluster, while then we have here a huge hypercluster in orange, which connects the different clusters. So to conclude, what we did in this paper is that we proposed a 2-step algorithm to cluster multidimensional data. The methodology leverages on both tensor decomposition and the DBHT algorithm. And then when we apply this method to a multidimensional economic network, we find promising results. Further developments on this topic will be to extend the procedure to full dynamic network so that we can incorporate new information on the network and to find clusters quite really fast in a dynamic way. The second one will be to use the dynamic of the core tensor to make forecasts, and so to forecast the clusters in the future and also trading patterns. Finally, we want to correlate the clustering structure to some exogenous variables, especially for the cases in which when the geographical proximity or the economic growth of the countries do not explain fully the clustering structure. So this is all for me, and thank you very much for your attention.